that involves a parallel plate capacitor. Now, a parallel plate capacitor is a very, very simple object. It's two plates and they're parallel. That's it. Except typically what we do is this. I put a voltage on them. I've connected up this plate of the capacitor to a positive terminal of a power supply, and I've hooked up this plate right here to the negative terminal of a power supply. There's 6,000 volts potential difference between the two. So this plate is at 6,000 volts higher potential than this plate. So if there's a positive charge near the positive plate, it's going to feel pushed from the positive plate to the negative plate. And if it moves from the positive plate to the negative plate, it picks up energy. We can see that. If I take this little aluminum foil ball and I give it some positive charge by putting it near the positive plate, and I put it in the region between the two plates, it gets pushed towards the negative plate. And if I put it right here, it'll move from the positive plate to the negative plate. And when it gets to the negative plate, it's moving faster. Oh, but then it transfers charge from it to this plate. It becomes negatively charged. Then it's pushed from the negative plate to the positive plate, and it bounces back and forth. And each time it moves, it's picking up a certain amount of kinetic energy, and the kinetic energy it's picking up is from the potential difference that it's traversing. It's going from high potential to low potential, and it's picking up kinetic energy as it moves. If I take these two plates and I put them closer together, the potential difference between them is still 6,000 volts, but something's changed. Now I'm going from 6,000 volts to 0 volts over a much smaller distance. Net result, I have a higher electric field, and so the force on a charge will be significantly greater. Oh yeah, and now if I put this between the plates, it goes back and forth very, very quickly indeed. If I move it farther apart, the electric field gets weaker, and at some point, it's not enough to even pull the sphere back and forth. Moving them closer, stronger electric field starts to move closer, electric field gets stronger, force gets bigger, and it makes that change of energy over a much shorter distance. That's a bit about a parallel plate capacitor. Now let's look at a problem that involves one. Let's take a look. Let's start by extracting some information from the problem. We've got two circular metal plates that form a capacitor, and the plates are separated by a distance of 4 centimeters. Okay? Now, the plates are charged up to 1,000 volts. So we have a parallel plate capacitor charged up to 1,000 volts with a separation between the plates of 4 centimeters. A proton is released at the positive plate, and we know it's going to travel to the negative plate. And we're asked to solve for the following things. We're asked to find the magnitude of the force on the proton, and we're also looking for its kinetic energy when it reaches the negative plates. Okay, that's the crucial information from the problem. Let's go ahead and solve it. And we're going to start by drawing a picture. And the picture will help us remember a couple of things about parallel plate capacitors. Okay, I've got two plates which are separated by some distance, and then we charge it up to a certain voltage. And what that means is this. Charges accumulate on the plates. I have a positive charge on one plate, I have negative charges on the other plates, and there's a potential difference between the two sides. And we know that the positive plate is going to be at a higher potential than the negative plate. There's also an electric field between the plates. Electric fields always go from positive charges to negative charges, so it goes from the positive plate to the negative plate. We also know for a parallel plate capacitor that the field is uniform in the region between the plates. And so we've got a region of uniform electric field. The first part of the problem asks us this. It said, what is the force on a proton which is released at the positive plate? So let's suppose we put a proton in here at the positive plate. And we're going to ignore any contribution of that proton to the field in the region between the two plates. That's a reasonable assumption. But the proton is clearly going to feel a force towards the negative plate. It's going to feel a force in this direction. What's the magnitude of the force? Well, to calculate the magnitude of the force, the easiest thing to do is to use the concept of the electric field, because the force on the proton is just equal to the charge on the proton times the magnitude of the electric field between the two plates. So to be able to solve this, we have to know what is the electric field in the region between these two parallel plates. And what is the electric field in that region? We'll give you some choices. We calculate the electric field this way. The electric field in a region between the two parallel plates of a capacitor is just equal to the difference in potential divided by the distance between the two plates. In this case, the electric field is thus equal to the potential difference, which is 1,000 volts, divided by the distance between the two plates. The distance between the two plates is 4 centimeters, or 0.04 meters. And so if we calculate delta V over delta D, we get a magnitude for the electric field, and it's this. The electric field is 25,000 volts per meter. But remember, the volt per meter is one unit for the electric field, but the other unit we have for electric field, the one we saw first, was the Newton per Coulomb. So the electric field is just equal to 25,000 newtons per Coulomb. And that makes it easy for us to do the next part of the problem, which is to calculate the force on the proton. Okay, the force on the proton is just equal to Q times E. That's the force on the proton. The magnitude of the charge on a proton is the same as the magnitude of the charge on an electron. It's just 1.6 times 10 to the minus 19th coulombs. The electric field, 25,000 newtons per coulomb. Multiplying out, we get a force on the proton of 4 times 10 to the negative 15th newtons. That's a pretty small force because it's a pretty small charge, but for something the mass of a proton, it will produce a significant acceleration. So the proton will start to move. And here's the next part of the question. It was, what's the kinetic energy of the proton when it gets to the negative plate? Now let's think about that. We've got two plates here. We've got one that's charged positively, one that's charged negatively. If we release a proton at the positive plate, it's feeling a force towards the negative plate. And so the proton will move from the positive plate to the negative plate. So it starts life there and ends up at the negative plate. But when it gets there, it's picked up some speed. It's got some kinetic energy. It's going to be moving towards the negative plate. The next part of the question asks us, what is the kinetic energy of the proton when it gets there? Well, we'll solve this by thinking about the difference in potential. Energy is conserved for this kind of system as it is for any system that we've seen. And so we can say this, the initial kinetic energy of the proton plus its initial potential energy, which is going to be Q, the charge on the proton, times the potential, remember, that's what we mean by potential, is equal to the final kinetic energy of the proton plus Q times the final potential. We're looking for the final potential energy of the proton. That's just equal to the initial kinetic energy of the proton plus the charge on the proton times the initial potential minus the final potential. Well, the initial kinetic energy of the proton is just 0. The charge on the proton is the same as the charge on the electron, so we can put that in. That's 1.6 times 10 to the minus 19th coulombs. And the difference in potential from the initial to the final is this. It's 1,000 volts because it goes from the plate which is charged positively to the plate which is charged negatively. It goes to a lower potential and it drops by 1,000 volts. It's a 1,000 volt power supply. But remember, we can write the volt differently. We can write the volt as a joule per coulomb. And then when you multiply that by a charge in coulombs, you get an energy in joules. And I get 1.6 times 10 to the minus 16th joules. There's a different way that we can think about the problem. And we can use the concept of the electron volt. Let's think about the problem again. So the proton goes from the positive plate to the negative plate. And as it does that, it goes through a difference in potential. And that is why it's losing potential energy. It's going to a lower potential, and so therefore it's going to a lower potential energy. And since it's going to a lower potential energy, it goes to a higher kinetic energy. So as the proton moves, it changes potential, and so therefore changes potential energy and changes kinetic energy. We know the difference in potential that it goes through is just equal to 1,000 volts. It starts out with the initial kinetic energy of 0. It doesn't have it, it's not moving. Question, what is the final kinetic energy of the electron? But let's not compute it in joules. Let's compute it in electron volts. What is the final kinetic energy in electron volts? And you want to do this without doing any computation. What is the final kinetic energy in electron volts? Think about it. We'll give you some choices. The proton has the same magnitude of charge as the electron. When an electron goes through a potential difference of 1 volt, it changes its potential energy by 1 electron volt. So when the proton goes through a potential difference of 1,000 volts, it loses a potential energy of 1,000 electron volts. And so therefore it picks up a kinetic energy of 1,000 electron volts. So we can solve it that way without doing any calculation. But then we can put that number in joules. 1 electron volt is 1.6 times 10 to the minus 19th joules. So 1,000 electron volts is just 1.6 times 10 to the negative 16th joules. Now that's exactly the same number as we got previously, and that gives us confidence in our answer, which is important, as we'll talk about next. Doing an assessment for a problem like this is slightly more complicated. I've released a proton on one plate, it goes to the other plate. What's its kinetic energy when it gets to the other plate? It's hard to get a physical feeling for that. So we treated the assessment differently. We solved the problem one way using the concept of potential difference. We solved it a second way using the concept of the electron volt. We ended up with two answers that were exactly the same. Doing the problem two different ways gives us the same result, gives us confidence in our answer, which is in fact correct. Not a surprise. Physics is about the world around us.